All right, if you're writing any kind of concurrent code in Go, you really need to listen up. This is, and I'm not exaggerating, one of the most common and dangerous traps you can fall into. So let's get right into it. This right here, yeah, this is the stuff of nightmares for a back-end developer. It's not just some random error message, you know? This is the actual sound of your production server melting down under heavy load, taking all your user requests down with it. So, have you ever seen this? Be honest. It is the unmistakable sound of your server crashing. If you've been doing this for a while, you're probably nodding your head right now. And if you're new to this, well, spoiler alert, you're going to see it. It's like a rite of passage. But really understanding why it's happening, that's what makes all the difference. So where does this all come from? Well, the root of the problem is a really basic truth about one of Go's most popular data structures, the standard map. It's just not thread safe, period. It was never ever designed to be poked and prodded by multiple Go routines at the exact same time. Just picture this for a second. You've got one Go routine trying to write to your cache, and at the exact same microsecond, another one is trying to read from it. What happens? The memory just gets completely scrambled. Now, here's the interesting part. Go could just let that happen, right? And you'd end up with this silent, weird data corruption that would drive you crazy trying to debug later. But it doesn't. Instead, it chooses to panic, to crash loudly and immediately. It's basically saving you from a much, much worse headache down the road. Okay, so how do we fix this? When you're not trying to pass data between Go routines, but you're trying to protect a shared piece of memory, like a cache, a channel isn't really the right tool for the job. No, what you need is a lock. You need, well, a digital bouncer. And that brings us to the sync.mutex. Mutex stands for mutual exclusion, and its job is actually super simple but incredibly powerful. It makes sure that only one Go routine gets to touch a piece of memory at any given time. Everyone else, you gotta wait in line. Simple as that. And when you look at the code, it seems almost too simple, right? Before you touch the map, you call mu.lock. When you're done, you call mu.unlock. It's like the bouncer lets one Go routine in, waits for it to finish, and then shows at the door before letting the next one in. Problem solved. Or is it? Not quite. Because this seemingly simple fix, it opens the door to something way more sinister. It's a silent killer that won't give you a nice, clean panic message. Nope, it will just freeze your entire application. Solid. And we call this a deadlock. The concept is shockingly simple, but absolutely deadly in practice. If you lock a mutex, but forget to unlock it, you've just created a permanent roadblock. Every other part of your app that's waiting for that lock is now just stuck, waiting forever. And this slide right here perfectly shows how incredibly easy it is to make this mistake. Just look at the dangerous code on the right. A Go routine grabs the lock, but then, bam, it hits an error and returns early. That mu.unlock call way down at the bottom, it's never going to get called. The lock is now held forever. And what's the result of that one missed line? Your application is now frozen. Forever. There's no crash, no helpful error logs, just silence. It's technically still running, but it's not doing a single thing. And let me tell you, this is 1,000,000 times harder to debug than a straightforward crash. Okay, so this is the #1 rule. If you take one thing away from this explainer, let it be this. The absolute instant you type mu.lock, your very next line of code, without fail, must be defer mu.unlock. Using defer is like a guarantee. It promises that the unlock function will be called as soon as the current function exits. It doesn't matter how it exits or where. Seriously, no exceptions. All right, so we've made our code safe from crashes and we've dodged the dreaded deadlock. Awesome. But we've just created a new problem, performance. Think about it. If you have 100 Go routines that just want to read the same value from a cache, our standard mutex makes them all get in a single file line and go one by one. That's a massive bottleneck. For this kind of situation, we need a more specialized tool. And that tool is the sync.rw mutex, or the reader-writer mutex. It's built on a really logical principle. It's totally safe for lots of people to read the same thing at the same time, but writing has to be an exclusive one-at-a-time deal. So it lets an unlimited number of Go routines grab a read lock simultaneously, but it will only ever grant a write lock to one. And the little dance it does is actually pretty clever. So as long as everyone is just reading, Go routines can come and go as they please. It's a party. But the second a writer shows up and asks for a lock, The bouncer puts up the velvet rope. No new readers are allowed in. Then it just waits. It waits for every single reader who's already inside to finish what they're doing and leave. Only when the room is completely empty does it let the writer have exclusive access to the whole place. Now, that sounds like the perfect solution, right? The best of both worlds. But all this extra power comes with its own complicated set of rules, and you guessed it, more dangerous traps. If you use an RW mutex the wrong way, you can end up right back where you started, with a deadlock. And this is the single biggest trap you can fall into with an RW mutex. A Go routine that's holding a read lock cannot just upgrade it to a write lock. It's not allowed. Go actually forbids you from doing this, and for a very, very good reason. Let me walk you through exactly why. Imagine Go routine A and Go routine B both have read locks. They're happily reading away. Now Go routine A decides it needs to write something, so it tries to get a write lock. What happens? It has to wait for Go routine B to release its read lock first. Makes sense. But what if Go routine B also decides it needs to write? It tries to get a write lock, and now it has to wait for Go routine A to release its read lock. See the problem? They're both stuck waiting for each other, forever. That's a classic deadlock. So the only safe way around this is to follow a very specific pattern. You have to completely release your read lock, then go back and acquire a full write lock from scratch. But, and this is the tricky part, in that tiny window where you held no lock at all, another Go routine could have swooped in and changed the very data you were about to modify. So after you get the write lock, you have to check your data again to make sure the situation is still what you think it is. This is called the double check pattern. And last but not least, let's talk about the performance trade-off. The RW mutex isn't magic. All that coordination of readers and writers adds overhead. It's a bit more work for the runtime. So you have to remember this. An RW mutex is only faster if your workload is massively skewed towards reading. If you've got, say, a 50-50 mix of reads and writes, a simple standard mutex is actually going to be faster, less overhead. Okay, let's wrap this up with the key rules for your concurrency toolkit. Rule number 1, maps are not thread safe. You have to protect them. Rule 2, always, and I mean always, defer your unlock. No excuses. 3, only reach for an RW mutex when your reads crush your writes in number. 4, never ever try to upgrade a read lock to a write lock. And finally, Rule 5, always double check your data after you acquire a write lock. Look, mastering the mutex is a fundamental skill for any Go developer, for sure. It gives you this incredible power to manage shared memory safely, but it also puts all the responsibility for not messing up and causing a deadlock right on your shoulders. And that leaves us with one last really interesting question. What if there was another way? What if you could use a data structure like a map that just protected itself? We'll dig into that next time.